Alright, so this will be a video on the cross product, and last video on the dot product I threw a lot of terms and a lot of material out there, and I'm actually going to work like some applied problems of dot product because I kind of got into that right away. Maybe I shouldn't have. I'll make sure to do a dot product and a cross product problem video, I guess next or whatever. But basically, the cross product is the second way you can multiply vectors, and this is the one where you don't get a scalar, you get a vector as the result of the multiplication. And so basically here, I just made up some more vectors as I usually do. You have 2, 1, and 3 for A, and then you have 0, 2, and 1 for vector B. Now, the cross product is the way you compute it when you have the unit vectors is not as straightforward as the dot product one. You have to take into account the unit vectors and then the components of each one. And so I'll be working that in a second. Basically, over here, I've drawn what the geometric interpretation of the cross product is. Basically, let's just I drew a plane, and basically I just with dotted lines. This is a plane. You have a vector A, vector B. You kind of think of it like like this. If my hands are pointing out like this, let's just say these are the vectors. And so basically, the cross product of the two vectors would be like this. Of course, I don't have 3 hands to show you, but basically you go from this my hands like this, and then the cross product would be what my marker is right now. That would be the result of the cross product. And basically, because the way it's the geometric interpretation of that is you have A cross B, and it's the magnitude of A times the magnitude of B times the sine of theta and the unit normal vector. And what does that mean? Basically, a normal vector is basically any vector that's perpendicular to the plane. So like this is perpendicular. I could have draw another one like this. That's a normal vector. That's a normal vector. That's a normal vector. Basically, all of these are normal vectors, and they can be of arbitrary. They can be of arbitrary length. And so really, as long as they're perpendicular to the plane, that's a normal vector. And so that's why in the definition it's important to include that, I think. You may not always see in textbooks, but that's really what's going on. It really helps drive the point home that the results, when you do a cross product of A and B, the result is a vector. And so the way you compute the component form of this, like I said, it's not as straightforward. So I have a 3x3 matrix here, and basically, if you guys are not familiar with matrices, you want to find the determinant of the determinant of the matrix will give you the cross product. And the way to do the determinant of a 3x3 matrix, you have a I'm just going to do an example. Basically, you break it up into 3 separate 2x2s, and so the way you do the first one is for the I component, you basically remove this row and this column. So basically, ignore the J and the K, or actually ignore the I, J, and K, and ignore the first column as well. Ignore I, A1, and B1. So really, the first one just becomes A2, A3, B2, B3, all of that in the I direction, and then for the J, you have to subtract. That's important to not forget the minus sign. And so you subtract from that, and so now for the J component, you get rid of the I and the K column, so these go away. Actually, no, I said that wrong. You get rid of this, and then so for this you would have A1, A3, and then you have B1, B3, all that in the J direction, and then the K direction would be A1, A2, B1, B2, and all in the K direction. And so to apply this to this problem, we're going to get, so A2, well, let me just write the whole thing out. So we have I, J, K, and then you have 2, 1, 3, 0, 2, 1. And so this would be, this is our matrix, and we want to compute the cross product of these components. And so for the first matrix, you would get, okay, so the first matrix would be 1, 3, 2, 1 in the I direction, and I'll get to in a second how what I do inside the 2x2s, and so we're gonna, and for the next one we're gonna get 2, 3, 0, 1 for the J, and then I guess I'm gonna go around a room here. I'll come back to what I wrote there in a second. And then in the K direction, we're going to get 2, 1, 0, 2. That's the K direction. And so what you do is you go diagonally. So first you do this times this, and so you do 1 times 1. and from that you subtract 2 times 3, and that will be in your I direction, and then of course subtract everything here. So 2 times 1 and 0 times 3. So you're subtracting 2 for the j direction. So 2, 1, and 3 times 0. You start with the leftmost, and then you cross it, and then you cross this one. And when you cross, make sure you subtract this diagonal from that diagonal. So we get 2j. I'm shortcutting it a little bit. And then in the k, we're gonna have 2 times 2, which is 4, and then 1 times 0. So it's 4. And so if we just kind of like do a little algebra here, so this is 1 minus 6, and so this is minus 5i minus 2j plus 4k. And so that would be the result of the cross product of these two vectors. And so, you know, in the x direction, or really I should say the I direction, but typically the I unit vector applies to the x direction. So you have negative 5 in that direction, minus negative 2 in the j direction, and a 4 in the k direction. And of course, you know, just so we practice the other alternative notation, it can be negative 5, negative 2, and 4. That will be the result of the cross product. Now, before I erase what I have here, basically, the cross product is interesting because it's not like the dot product, which is just commutative. You know, for the dot product, you can have, you know, a, b, we have 3 vectors, a, b, and c. I know a times a dot b dot c is the same as a. I should write it a different way. A dot b dot c, like parentheses like that. The cross product is actually anti-commutative, and if you're not familiar with that term, it basically just means this. So you have a cross b. Just draw the little vector hats on all of these, because these are vectors that I'm, you know, multiplying. And so a cross b is actually equal to the negative of b cross a. That's what anti-commutative means. You know, you have one on one side, you have the relationship, and then when you switch the two, I guess I'm not even sure if arguments is the right term. If you switch these two letters, the anti-commutative, you put the negative sign in front of them. That's basically what it means. And so that's kind of an intro to the cross product. Just to kind of recap, you know, the result's always a vector when you multiply them. And if you want the cross product of 2 vectors, the result's always going to be a vector. And so, and basically, and also the result of it is always perpendicular to both of these vectors, because it's a normal vector to the plane. And these are normal vectors, that's a normal vector, that's a normal vector, and you know, this is a normal vector, that's a normal vector. As long as it's perpendicular to the plane, it's a normal vector, and that's always the direction the cross product's in. And so, and another thing is, like, so if you, I should probably put a theta here, that would have definitely, yeah, it's always the angle between the 2 vectors whenever you're doing any kind of like vector operations. Just keep that in mind. It's not like some arbitrary angle. And actually, it's even better to say this. Actually, when you do the cross product of A and B, there's something called a right-hand rule. And so basically, you know, you essentially kind of like curl your hand in. I'm not even sure how you do it again. It was always kind of weird when I was learning it. But basically, the smallest possible angle you can have between the 2 vectors, and that is the angle that you use when you're doing the geometric version. And of course, if you want to do B cross A, this vector would actually be pointing the opposite direction. So if we'll just, you know, draw this over here, you know, you have A, B. If you want to do B cross A, it would actually be down. The vector would be pointing down here. You know, just pretend the plane. Just this is the plane, and then just like that, and then let's probably just cut it off here. So yeah, you should have the vector going this way, and of course that's the angle between them. Now, if you did, that's what happens if you do B cross A. Yeah, because it's opposite. Anyway, so that's pretty much a good stopping point, and in the next video I'll be doing a problem that involves the dot product, and then the video after that I'll do one that involves the cross product. So that's all for now, and I'll see you guys in the next video.